In this video, I'll be explaining to you about relative frequency. Let's start off by firstly revising what we learnt about theoretical probability. This is the probability of an event which is equal to a number of favorable outcomes over the total number of outcomes. An example of this might be involving a bag that contains 3 blue, 2 green and 1 red marble. So altogether there are 6 marbles, but the probability of a blue marble in this case would just be 3. This simplifies to get an answer of half. Okay, so this is a theoretical probability based on what there is, okay, which is the total number of outcomes, and what we want, which is the favorable outcomes. This is a totally different answer to what we'll get in experimental probability. So if I was to use exactly the same bag, okay, with 3 blue, 2 green and 1 red marble, okay, I would get a different probability of getting blue. Now, this is to do with experimental probability. So if I perform this experiment, the probability of an event happening is equal to the number of times the event happened over the total number of trials. So looking at this table that we have here, the number of times we have blue is 7 times. So we're going to write 7 because that's the number of times it happened. Over the number of trials. So this frequency column tells me how many times I've gotten each of these, but also the total of this, which is the number 13, that tells us how many times we've performed this experiment where we got the marble out of the bag and we put it back in and restarted the event again. So it's 7 out of 13, which is not equal to half as what we got before. Okay, this is experimental probability, okay, based on a real life scenario of performing this experiment. Now, expected frequency is another concept we have to know, and that is the expected number of times an event will occur over the repeated trials. So expected frequency is involving the theoretical probability times the number of trials. So basically from this example here, if the chance of me getting blue was half, and I pick out like any kind of marble in there, okay, 100 times, the expected number of blue marbles out of those 100 times will be the probability, which is half, times 100, which is 50. Okay, and we're going to look at these more examples later on. Okay, so make sure you copy this bit down. All right, and I'll move on to some examples now. For example 3, Connor tossed a coin 100 times and recorded the results in a table. Calculate as a decimal, part I, the experimental probability of tossing a head. Okay, so we're looking at experimental probability here. So that means we can only look at the table, and the probability of getting a head out of that table is 46 out of the token frequency of 100. So we're just going to write that down. All right, and our theoretical probability of getting a head, okay, so that's what it's asking for, is half, right? Okay, and it's a half because, well, there's 2 sides of a coin and 1 side's heads. Question B, are the experimental and theoretical probabilities similar? Well, the probability of a head experimentally is 0.46, so this is 0.5 for the theoretical one. So it is similar, okay, so we're just going to say yes for that because they only differ by a difference of 0.04. That's not very much at all. But let's have a look at C now. For 100 tosses, what is expected frequency of heads based on the theoretical probability? How does this be compared with the actual number of trials? So the expected frequency is basically how many times we expect heads to come up when there's 100 tosses. So that's equal to half times 100. Okay, half being the chance of me getting a head out of tossing the coin, and times by the number of trials. So that would equal to 50 times, right? Now, is this similar to what they have in the table? So I'm expecting 50 heads here, but they've got 46 heads. So yes, it is close. Okay, so we're just going to say this is similar to what is obtained from the experiment. All right, let's move on to example 4. Brianna rolled a die 200 times and recorded her results. So we can see here that on a die, you can get the results 1 through to 6, and it seems like there are different numbers of each outcome. Find the experimental probability of rolling an even number. So we know even numbers are simply 2, 4, and 6. So there you go, 2, 4, and 6. And if we add the total number of 2s and 4s and 6s, so 40 plus 24 plus 34, we do get a total of 98. And we divide this by the number of trials, which is 200 times. Okay? Now that simplifies to give you 49 over 100, or you can write 0.49. Both are acceptable. Part 2 says an even number or a number greater than 2. So if they are even numbers, then I'm going to be highlighting these ones. But numbers greater than 2, okay, also include 3, 4, which is highlighted, and 5. Okay, so I'll have to add all these up. Now, if I add all these numbers up, I will get 162. Or simply get 200 subtracted by that number. Right? That's the quick way. So 162 over 200 would equal to 81 out of 100. Okay? Next one. The probability of an even number and a number greater than 2. So, if we're looking at even numbers that are greater than 2, then 2 is not acceptable because that's not greater than 2. The first number that is even and greater than 2 is the number 4, and followed by number 6. So we're going to total 2 of these numbers here, 24 and 34. And we also write the probability of even and greater than 2. So I'm just reminding you that this means greater than, less than, and you're allowed to use this in the notation for probability. When you see this symbol, it means greater than or equal to. And this sign means less than or equal to. Okay? Now, we're looking at these two numbers only, and they total up to become 58 out of 200. So that simplifies to give us 29 out of 100. Okay? Part 4. The probability of even and not greater than 2. So if I have all the highlighted even numbers, they are 2, 4, and 6, okay? But you also need to agree, okay, I'll choose the ones that agree with the fact that they are not greater than 2. So this is not greater than 2 because it is 2, okay? You don't want this one because it is greater than 2, and this one also. All right, so you only want to choose the ones that are not greater than 2. So it's 2 or below, basically. And that is just the number 40 out of 200, which does simplify to give you 1 out of 5. Part B, part I, calculate the probability of rolling a 5 or 6. Okay. If it's 5 or 6, we have to include both of them, right? So 5 or 6 includes 34 and 35. That totals up to become 69 out of 200. Now this is based on experimental probability though. But what if now I calculate this as theoretical probability? Well, out of the numbers 1, 2, 3, 4, 5, and 6, 5 and 6 are 2 numbers out of the 6 numbers. So the theoretical probability is 2 out of 6. Right? Question C. What is the expected number of trials of rolling a 5 or a 6 in 200 rolls of a die, how does this compare with Brenner's observed number of times? So if I get the numbers 2 out of 6, okay, which is the probability or theoretical probability of getting a 5 or 6, and we multiply that by the number of trials, which is 200, we would get 66 and 2/3. Okay? So we will be expecting around, if I was to round this up to the nearest whole number, we'll be expecting around 67, 67 number of 5s and 6s. And if we have a look at what we got before, which is our experimental probability, that's 69. So how does it compare? We can say this is close. Okay? So we can say which is close to 69 for the experimental probability or experimental result frequency. Okay?